This is the multivariable regression video that provides details about what regression coefficients really mean. For regression with a single predictor, the regression coefficient has a simple visual interpretation. That is, it's the slope of the line that's fit to the scatter plot of y versus x. Unfortunately, for multi-predictor regression, this won't be the case. This video is intended to provide you with an intuitive explanation of what the multivariable regression coefficient really means. To keep things simple, I'll stick to the case of two predictors, but everything that you'll see here easily generalizes. What we'll eventually discover is that the coefficient in the multi-predictor regression model, these are sometimes called beta coefficients, partial regression coefficients, or just regression coefficients. That coefficient is the slope of a line corresponding to a scatter plot. It just isn't the scatter plot of the predictor xk versus the outcome y. The main reason that this distinction is important is it provides an intuitive explanation of what can go wrong when the predictors are highly correlated. To create a partial regression coefficient for the second predictor x2, say, start by fitting the usual regression line with the observed y as the outcome and the observed x1 as the predictor. This line will explain some of the variation in outcome, denoted by the sum of squares for model with the subscript of 1, and leave some of the variation in the outcome unexplained, denoted by sum of squares error 1. This is a visual depiction of the process. The residuals are the thing are going to be passed to the next stage of modeling. The previous regression line dealt with the impact of x1 on the outcome, but didn't deal with the possible correlations among the predictors. To account for this latter issue, it turns out that the thing to do is to fit a model with x2 as the outcome and x1 as the predictor. This is a visual depiction of the process. The residuals are going to be passed on to the next stage of modeling. Now all of the impacts of x1 have been accounted for. At the final stage, we still fit a model with a predictor and a response. The predictor is an x2, but instead is the residual of x2 after accounting for the contribution of x1. The outcome isn't y, but instead is the residual of y after accounting for the contribution of x1. This line will explain some of the variation in outcome, denoted by SSM2, and will leave some of the variation outcome unexplained, denoted by error sum of squares with a 2. This is a visual depiction of the process. The regression coefficient is the slope of the line that corresponded to the previous scatter plot. This scatter plot is sometimes called a partial regression plot. This slide illustrates that the amount of variation explained by the model increases from step to step. The amount of variation that remains unexplained at the final step becomes the sum of squares for error for the overall model. This process can be repeated for each of the predictors in turn, thus generating the entire set of partial regression coefficients. The order that the predictors are entered into the model doesn't really matter. And this slide illustrates the point. As should now be clear, the scatter plot of y versus xk and the partial regression plot for xk will differ to the extent that xk is correlated with the other predictors, and also to the degree that xk is correlated with the outcome. The more the scatter plot and partial regression plot differ, the greater will be the difference between the univariable and multivariable regression results. Following up on this idea, technically speaking, partial regression coefficients for models that include different sets of covariates aren't directly comparable. How much to worry about this is something that has to be addressed on a case-by-case basis. Following the logic of this video, you should worry more when the covariates in question are strongly predictive of outcome and or are strongly correlated with the predictors in your model.